Look down at your hand, flex your fingers, that solid weight. The reason you are pinned to your seat right now has a name: mass. Simple, right? Case closed. Except the best theory of the universe says your particles shouldn't have any mass at all. They should be weightless ghosts. This isn't a fun fact. It is the Yang-Mills mass gap problem. The Clay Institute placed a $1 million bounty on solving it. No one has touched it. You are made of an unsolved mystery. Let's open it. Back in the year 2000, a rich math institute did something unusual. They took the 7 hardest unsolved problems in mathematics, puzzles that had stumped the best minds for generations, and placed a $1 million bounty on each. Solve one, get the cash. Simple. 7 problems, $7 million. You'd think that would light a fire under every genius on Earth, and it worked, kind of. One problem, the Poincaré conjecture, did get solved. But the man who solved it, Grigory Perelman, looked at the $1 million and said, "No thanks." Then he vanished from mathematics, which makes this the only time in history someone was too smart to take $1 million. Now 6 problems remain, and one of them is Yang-Mills' existence and mass gap. That's the problem that explains why particles have weight, why your coffee mug stays on the table, why you don't float away. Here's the strange part. Every particle physics experiment ever done assumes this problem has an answer because the math works in practice, but no one can prove it works on paper. Wait. So we base entire technologies on an unproven guess. Yes, that's exactly what we're doing. So the prize is still out there. The job posting is still open. Requirements: a brain that can bend abstract math, a high tolerance for dead ends, and a willingness to become a millionaire or refuse the cash and become a legend. It's a help-wanted sign for the smartest person alive, and no one has applied. But of the 6 remaining problems, Yang-Mills might be the most important, because if we can't prove why matter has mass, we don't really understand the stuff we're made of. We're just borrowing the math and hoping nobody notices. Let's rewind to where this problem came from. You've seen the atom drawing your whole life. The glowing ball with tiny dots spinning around it like miniature solar system. Teachers love it, but it's a lie, a useful one, but a lie nonetheless. Here's the truth they skipped. That glowing ball in the center isn't solid. It's a tiny cluster of even smaller pieces. Zoom in past the atom, past the nucleus, and you find quarks. Quarks are the real fundamental building blocks. They're like the little bumps on a Lego brick, the parts that stick together, but there's no brick underneath. Just the bumps. Only 2 kinds matter for everyday stuff, up and down. 3 quarks make a proton, 2 up, 1 down. 3 quarks make a neutron, 2 down, 1 up. That's it. That's the recipe for your entire body. Wait, 3 quarks, all with the same electric charge, should blast apart like magnets forced together. So why don't they? Because nature invented a stronger force, the strong force, and it's carried by particles called gluons. Gluons are the glue. They stick quarks together so hard you can never separate them. Try to pull one out and the force gets stronger the farther you pull, like a rubber band. Pull hard enough, and the energy you put in creates a new quark. Quarks are permanently trapped. Okay, so you've got quarks making protons and neutrons, gluons holding them together. That's the engine inside every atom. Now here's the part that breaks your intuition. Quarks and gluons aren't tiny balls. They don't have a size. They're more like concentrated energy knots, held together by a force that gets stronger with distance, the exact opposite of everything else in your life. That backwards behavior is described by a set of equations written in the 1950s by 2 physicists, Chen-Ning Yang and Robert Mills. Their theory was elegant. It predicted how particles like gluons interact, but it had a problem. When they ran the math, the equation said the force-carrying particles should have 0 mass. But in the real world, the strong force only works across tiny distances inside the nucleus. That short range implies the gluons should have mass. Something gives mass to these particles, something the math doesn't account for. That missing something is the mass gap. So we have perfect equations that describe the pieces of the universe, but they leave out one critical number, and that missing number is worth $1 million. Let's look at what Yang and Mills actually wrote, and why it broke the universe. Hands up if you've ever held something that weighs nothing. Your hand isn't up, obviously, because nothing weighs nothing. Empty space weighs nothing. A vacuum weighs nothing. But a particle that actively does something, that should weigh something. Now meet the gluon. The gluon is the messenger of the strong force. Every time two quarks need to stick together, a gluon zips between them carrying the command, stay close. It's the postal service of the atomic nucleus. And in the math written by Yang and Mills in 1954, that postal service operates using absolutely weightless mail. Let that sink in. The equations predict that gluons have exactly zero mass, not a little bit, zero. The same weight as a shadow. Now, when you have a force carried by a weightless particle, something weird happens in physics. The force becomes infinite in range. Light can travel across the universe because photons have zero mass. Gravity can reach across galaxies because the hypothetical graviton would also be massless. Those are long-range forces, but the strong force is not long-range. It only works inside the nucleus, a distance about 1,000 times smaller than the atom itself. If the strong force reached across the kitchen, your coffee mug would be permanently glued to the counter. So here's the contradiction. A massless particle carries a short-range force. That's like ordering a pizza delivery from the other side of Earth that somehow only reaches your driveway. Something is clearly wrong with the math, or missing from it. That missing piece is the mass gap. The difference between the zero mass the equations predict and the actual mass the gluon must have to make the force only work at tiny distances. We know it's there. We can even measure its effects. But no one can prove the equations allow it. This is the universe's most embarrassing math error. A 70-year-old scribble that says zero when everything in reality says nope, and you can't just fix it by adding a number. The equations are so precisely balanced that any change breaks the whole thing. The mass gap has to emerge naturally from the math itself, like a puzzle piece that only fits if you fold it along the right lines. That's why the $1 million is still on the table, because we all know what the answer looks like. We just can't prove it sits inside the equation. Next, exactly why this drives physicists crazy, and why the solution might be even stranger than the problem. You already know the answer. It's the most famous equation in physics. E equals mc squared. Energy equals mass. Gluons have zero mass on paper, but they're drenched in energy from their own interactions. That energy, Einstein showed, is mass. So the mass gap is just energy hiding in plain sight. Problem solved. Except, no, not even close, because that makes sense is not a mathematical proof. A proof is a chain of logical steps that starts with the equations of Yang and Mills and ends with the mass gap automatically emerging. Not we know it's there, so the math must allow it. You need to show it cannot be any other way. Picture a locked chest with treasure inside. You can see it through the keyhole. You can even guess the key's shape, a plus sign with 3 bumps. That's intuition. But the prize is for forging the actual key from metal, proving it fits and turns. Why is forging that key so hard? Because the equations for gluons are non-linear. The force feeds itself, creating a loop. Every time physicists calculate what happens inside a proton, the math gives infinite answers. They use renormalization, surgically removing infinities to get finite numbers. It works, but it's like defusing a bomb while wearing oven mitts. The mass gap is buried in that infinite mess. If gluons were truly massless, any tiny nudge would create a ripple that never stops, like plucking a guitar string that rings forever. But that doesn't happen. The strong force has a minimum energy threshold. You have to push hard to even get started. That threshold is the mass gap. The equations don't forbid it, but they don't enforce it. The proof must show they force it. We know the gap exists because protons exist. The universe clearly figured it out. But translating that into a rigorous mathematical derivation, showing exactly where the gap comes from, has stumped everyone since the 1950s. So the Clay Institute's prize isn't for saying it's energy, it's for writing the instructions, the chain of reason that starts with the equations and ends with the gap. Those instructions remain unwritten. Next, what is actually missing from the math, and what it means if that gap can never be found? You are standing on a staircase. The first step is floating 6 inches above the ground. You can't just walk onto it. you have to jump. This is the mass gap. The equations of Yang and Mills predict that the lightest possible particle should weigh exactly 0. That's the ground floor, but experiments and logic both scream that the first real particle, the lightest one nature allows, weighs something, and more importantly, that weight is not 0. It is strictly, rigorously, provably positive. So the staircase doesn't start at the ground. The first step is already above it. The distance between the ground and that first step is the mass gap. Now, the actual requirement on the Clay Institute's website says this. You need to prove that the lowest energy state in the Yang-Mills theory is separated from the first excited state by a positive number. In other words, no particle can be arbitrarily light. There is a floor, and the floor is not 0. Think of a piano where the lowest key plays a note with a frequency of, say, 50 Hz. But the laws of physics say that key shouldn't exist. The lowest note should be 0 Hz, silence. The key is physically there, and you can hear it, but the math that describes the piano says no note can come from that key. The million-dollar question: prove mathematically that the key does not produce silence. Yes. $1 million to prove the piano doesn't start at 0. It sounds like a joke. It is not a joke, because the math currently allows a scenario where the lowest note is 0, where the strong force has infinite range, and the universe would be a sticky, glued-together mess. That scenario has not been ruled out on paper. Only nature has ruled it out by existing. The proof must show that the theory forbids 0 mass particles. It must show that the staircase cannot possibly have a step at ground level. The step must be above ground, and the gap between ground and step must be a number greater than 0. That number, we don't even know exactly what it should be, but we know it has to be there, and nobody can prove it. So the challenge sits on that floating step, waiting for someone who can show it's not magic. The step is real. The math just refuses to hold it up. Next, why the usual tricks of physics all break against this wall, and how the answer might hide in a place physicists don't want to look. You're a quark. You live inside a proton with 2 other quarks. You want to see the world, so you start walking away. But the moment you move, something yanks you back, harder the further you go. It's not like gravity, which gets weaker with distance. It's like a rubber band that tightens the more you stretch it. And if you pull hard enough, the rubber band snaps and creates 2 new quarks out of the energy, so you're still not alone. You can never be alone, ever. This is confinement. Quarks only ever appear in groups of 2 or 3, mesons and baryons. A lone quark has never been seen. The universe is just really bad at letting go. Now you might think confinement is exactly the mass gap problem. After all, if quarks are permanently stuck together, then the lightest thing that can fly free is a proton, which weighs plenty. Surely that proves the mass gap. Nope. Confinement describes behavior. Quarks are trapped. The mass gap describes a number, the minimum energy threshold. They are related like a lock and a key, but proving one exists does not prove the shape of the other. Think of it this way. You know a staircase exists. You can see it, you can climb it, but that doesn't tell you how far the first step is from the ground. Confinement tells us the staircase is there. The mass gap asks, exactly how high is step number 1? Physicists have shown that confinement must happen from numerical simulations and experimental evidence, but a mathematical proof from the Yang-Mills equations, still missing. And without that proof, we can't be sure the 2 phenomena are even connected in the way we think. So we have confirmation, but no explanation. We know what happens, but not why the equations force it. Which raises an uncomfortable question. If the math can't explain the most obvious fact about the strong force, that quarks are stuck, what else is it missing? You built a machine that slams protons together at nearly the speed of light. It cost billions. It works perfectly. You can measure exactly what comes out. Now ask a mathematician to prove those measurements come from the Yang-Mills equations. They'll shrug, that's the gap. Physicists see confinement, they've measured it, they've simulated it. That's good enough to make predictions, build models, and win Nobel Prizes, but it's not a proof. A proof means starting from the equations and walking step by step to the conclusion with no leaps, guesses, or close enough allowed. And that walk, we can't take it. The sidewalk ends. Here's why. The math we normally use, calculus, analysis, assumes things are smooth and predictable, but Yang Mills is neither. Infinities explode everywhere. The equations involve fields that fluctuate wildly at tiny scales. Normal calculus treats space like a continuous sheet. But at the level of quarks, the sheet isn't smooth. It's a fractal mess of infinite detail. Physicists get around this by using approximations. They chop the infinite into chunks, calculate each chunk, and sum them up. It works for experiments, but it's like building a skyscraper with an architect who says this beam is roughly strong enough. The Clay Prize requires the architect to prove the beam can hold exactly, no guesswork. The smartest person to try this seriously was Edward Witten. He's the closest thing physics has to a wizard. He used ideas from string theory to map parts of the problem. He won the Fields Medal, math's highest honor, for work related to this, but even he couldn't close the gap. He showed that if certain assumptions hold, the mass gap appears, but he couldn't prove those assumptions from the equations alone. So the $1 million sits there. And here's the quiet fear among people who think about this. Maybe we need entirely new math to solve it. The tools we have aren't just rusty, they might be the wrong tools entirely. You can't chop down a redwood with a butter knife. And you can't prove the mass gap with 19th century calculus. So the prize waits. And every year that passes, the question gets louder. Is it even solvable, or is this just a monument to how much we still don't know? You're looking at $1 million. The problem is simple enough to write on a napkin, prove the Yang-Mills equations work and the mass gap exists. You've trained your whole life. You sit down, and you realize you can't even take step one. That's the moment the smartest people gave up, not because they ran out of ideas, but because they realized the ideas they needed don't exist yet. You'd think enough intelligence can crack anything. That's what makes this problem special. It proves that wrong. The math we have, calculus, analysis, was built for smooth, predictable things. The quantum world is not smooth. It's a raging sea of infinite detail, and our tools are rowboats. Edward Witten, the closest thing to a real-life wizard, came the closest. He reached into string theory, a framework that imagines 10 dimensions of space, and pulled out a glimpse of the answer. But a glimpse is not a proof. And even he couldn't finish. That's when the field went quiet. Not from defeat, but from clarity. Why pour years into a problem that demands a language no one knows how to speak when there are other problems that actually give ground? We spend billions on particle accelerators. We slam protons together at speeds that would make the universe blush. Every day, those experiments confirm Yang-Mills' predictions with pinpoint accuracy. Nature screams the answer, but a mathematician would still say, prove it. That's the absurdity. We have the answer in our hands, but we can't write down how we got there. It's like winning a race but not knowing how your legs moved. So the smartest have moved on. They shrugged, decided the price was too high, and left the $1 million sitting on the table. Unless, of course, someone out there is quietly inventing the math we need. And then the problem becomes a routine exercise. But until that happens, the mass gap remains the problem that beat the best. And that brings us back to you. You're sitting there, held together by a force the math says shouldn't work. The equations predict you'd fly apart, but you don't. That's the gap. The $1 million ghost sits, waiting. Not because the proof is impossible, but because no one's found the right lens yet. The shape of the key exists. We just can't see it. Maybe you will. Maybe you'll collect the check, join Newton and Einstein, and finally close the loop. If you do, leave a comment. We'd love to know who beat the problem that beat everybody. Thanks for watching.